Hello, everyone, and welcome. I'm excited to have you here today. Today, we will be exploring the functioning of modules. As this is our first slide, I'd like to briefly introduce what we'll cover. We'll look into how different modules work together, their roles, and how they contribute to the overall system. So, let's get started and dive into understanding the fascinating world of modules. Let's move on to slide 2, which covers the functioning of a computer. This is a crucial part of understanding how all the components work together seamlessly. When we talk about the functioning of a computer, we're essentially exploring how it processes data and executes tasks. At its core, a computer takes input, processes it using its various components, and then produces output. This process is continuous and highly efficient. The central processing unit, or CPU, acts like the brain of the computer, interpreting instructions and managing operations. It communicates with memory and other components to perform tasks quickly and accurately. Understanding this flow helps us appreciate how computers can perform complex functions, from simple calculations to complex simulations, all in a fraction of a second. This interconnected operation is what makes computers so powerful and versatile in today's digital world. Welcome to this introduction slide. Here, I want to set the stage for the discussion that follows. We'll explore the key points thoroughly, but in a way that's conversational and engaging. The goal is to highlight the most important concepts so they resonate with you. As we go through, I'll make sure to connect each point to the overall theme of our presentation, helping you see how everything fits together. This slide is all about laying a solid foundation for understanding what's to come. So I encourage you to think about how these ideas relate to your own experience and the bigger picture. A computer is an electronic device that many of us use daily, but what exactly does it do? Well, at its core, a computer can perform a wide range of operations. These operations are guided by a set of instructions known as programs. Think of programs as the computer's way of understanding what tasks to perform. This ability to follow instructions precisely is what makes computers so powerful and versatile. Throughout this presentation, we'll see how this fundamental concept of computers underpins many of the technologies we rely on every day. Let's take a closer look at the table comparing data and information. First, when we talk about data in computer terminology, we're referring to raw facts and figures. These are just basic pieces of information, like numbers or words that haven't been processed yet. Now, when we combine or organize this data in meaningful ways, it turns into information. So, information is essentially data that has been aggregated or summarized to give it context and significance. Next, the process is important to understand. Data is processed to create information, and then information can be further processed to produce meaningful data. It's a continuous cycle of transforming raw facts into useful insights. For example, if I tell you A1 Achal 2016 class, that's just raw data. But if I say, in 2016, Achal was the topper of our class, that's now meaningful information because it provides context and a story. Finally, it's crucial to remember that data are raw facts, and information is meaningful data. Recognizing this difference helps us understand how data becomes valuable through processing and interpretation, which is at the core of managing information effectively. Today, I want to talk about how a computer functions, which is fundamental to understanding how we use technology every day. So, what does a computer actually do? At its core, a computer processes data and performs tasks based on instructions. It all starts with input devices, like a keyboard or mouse, which allow us to give commands or data to the computer. Once the data is entered, the computer's central processing unit, or CPU, takes over. The CPU is often called the brain of the computer because it interprets and executes instructions. Next, the data is temporarily stored in memory, like RAM, so the CPU can access it quickly. This step is crucial because it speeds up processing and makes the system efficient. After processing, the computer may store the results in storage devices such as a hard drive or SSD, or send output to devices like a monitor or printer. This entire process, input, processing, storage, and output, happens very rapidly, allowing us to perform complex tasks seamlessly. Understanding this functioning helps us appreciate how computers are so powerful and versatile, supporting everything from simple calculations to complex simulations. It's this smooth coordination of components that allows computers to serve as incredible tools in our daily lives and work. Let's take a closer look at this table. It shows us the basic flow of how tasks are carried out, whether it's in cooking or in computing. On the left, we have the input, which is what we start with, like the ingredients for making batter or the data we want a computer to process. In the middle, there's the process, which is the actual work happening, like putting the batter in the oven or the computer executing a program. And on the right, we see the output, the final result, such as a baked cake or the information produced by a computer. What's really important here is understanding that every task, whether it's baking or computing, follows this input-process-output cycle. It's a simple but powerful way to see how things work step by step. For example, if you're making a cake, you gather your ingredients, then you mix and bake them, and finally you get your finished cake. Similarly, in a computer, you input data, the computer processes it, and then it gives you the output, like a report or a calculation. This cycle is fundamental because it helps us understand how complex systems, like computers, operate in a structured way. It connects directly to our overall theme of understanding how technology processes information by breaking it down into these clear, manageable steps. Recognizing this cycle makes it easier to grasp how computers solve problems and perform tasks efficiently. Let's take a closer look at the functional components of a computer. These are the building blocks that work together to perform all the tasks we ask of a computer. First, we have the central processing unit, or CPU, which is often called the brain of the computer. It processes instructions and manages operations. Next, there's memory, specifically RAM, which temporarily holds data that the CPU needs quick access to while working on tasks. Then we have storage devices like hard drives or SSDs, which store data permanently. Input devices, such as keyboards and mice, allow us to communicate with the computer, while output devices like monitors and printers let us see and receive the results of the computer's work. Connecting all these components is the motherboard, which acts like the nervous system, ensuring that everything communicates smoothly. Understanding these components helps us see how a computer functions seamlessly to perform complex tasks. Let's take a look at the functional components of a computer. At the heart of the system is the central processing unit, or CPU, which is often called the brain of the computer. It processes all the instructions and manages the operations of the entire system. Next, we have the input unit, which is responsible for taking in data from outside sources, like a keyboard or mouse. Then, there's the main memory, where data and instructions are temporarily stored for quick access during processing. Moving on, we have the output unit, which is used to send processed data back out to the user, such as displaying information on a screen or printing a document. These components work together seamlessly to make the computer function efficiently. Think of them as the essential building blocks that enable us to perform a wide range of tasks, from simple calculations to complex simulations. Understanding how these parts connect helps us appreciate how computers operate as integrated systems. Now, let's talk about the input unit. The input unit is essentially made up of the input devices that we attach to the computer to communicate with it. These devices are what allow us to feed data and commands into the system. Examples of input devices include the familiar keyboard and mouse, which most of us use daily. But there are also specialized devices like the magnetic ink character reader, or MICR, which is often used in banking for check processing. Then we have the optical mark reader, or OMR, which can quickly read marked areas on forms or surveys. The optical character reader, OCR, is another interesting device that can recognize printed text, converting it into digital data. There are also devices like joysticks, which are common in gaming but can also be used for other control applications. The key takeaway here is that the input unit comprises various devices that serve as the interface between us and the computer. These devices are crucial because they enable us to interact with and control the system effectively, which ties back to the overall theme of how different components work together to make a computer functional. The output unit is essentially the part of the computer that delivers information back to us. It's made up of the output devices that are connected to the computer system. These devices are responsible for presenting data in a form that we can understand and use. Some common examples of output devices include monitors, which display visual information, printers, which produce physical copies of digital documents, plotters, often used for large-scale drawings or designs, and speakers, which play audio output. These devices are crucial because they complete the communication cycle between the computer and the user. Without them, it would be impossible to see, hear, or otherwise perceive the results of the computer's processing. So, the output unit is essentially the final stage where the computer's work is made visible or audible to us. This ties into our overall theme of how computers process and deliver information efficiently and effectively. Now, let's take a closer look at the Central Processing Unit, or CPU, which is essentially the brain of the computer. It acts as the control center, coordinating all the activities happening inside. The CPU isn't just one simple unit. It has several key components, each responsible for specific functions that keep everything running smoothly. One of these components is the Arithmetic Logic Unit, or ALU. This part performs all the basic calculations, like addition, subtraction, multiplication, and division. But it also handles logical operations, such as comparing values to see if one is less than, greater than, or equal to another. The ALU is fundamental because it carries out the actual data processing. Next, we have the Control Unit, or CU. Think of the CU as the traffic cop of the CPU. It interprets instructions, manages the flow of data between different parts of the computer, and guides the overall operation. Without the CU, the CPU wouldn't be able to coordinate tasks effectively. Finally, there's the Memory Unit, or MU. This is where data is stored temporarily or permanently, depending on the type of memory. The capacity of the storage is measured in bytes, which tells us how much information can be held at once. The MU works closely with the other components to ensure data is available when needed. Together, these components form the core of the CPU, enabling it to process instructions efficiently and reliably. Understanding these parts helps us see how the computer's brain functions, supporting the overall theme of how hardware and software work together seamlessly. Today, I want to focus on the concept of memory. Memory is a crucial component when it comes to understanding how we process and retain information. It's not just about storing data, it's about how we encode, store, and retrieve that information when we need it. One of the key points to remember is that memory isn't perfect. It's susceptible to errors and distortions. Our brains are constantly filtering and reshaping memories based on new experiences and perceptions. This ties directly into the overall theme of how we learn and adapt. Effective memory techniques can enhance our ability to recall important information, which is essential for both personal growth and professional success. So, understanding the mechanics of memory helps us develop better strategies for learning and retention, making us more efficient and confident in tackling new challenges. Memory in a computer can be thought of as a collection of tiny units called cells. Each of these cells stores data, and they're made up of even smaller parts called bits. Now, a bit is the most fundamental unit of memory, and it can only be one of two values, 0 or 1. These bits are the building blocks, kind of like the alphabet of digital information. When we put 8 bits together, we form a byte. Think of a byte as the smallest chunk of memory that can hold a single character, like a letter or a number. It's really the basic unit we use to represent data characters in a computer. Beyond bytes, we have larger units of measurement for memory: kilobytes, megabytes, gigabytes, terabytes, and so on. These help us understand and quantify the amount of data a computer can handle. Understanding these concepts is key because it shows how data is stored and processed at the most fundamental level, which ties back to how computers operate so efficiently and effectively. Let's take a closer look at how digital storage units are structured and related. Starting with the smallest unit, we have the bit, which is short for binary digit, and that's the fundamental building block of digital data. Moving up, 8 bits make 1 byte, which is what computers typically use to encode a single character or a small piece of data. From there, the units increase in size by powers of 1024. For example, 1024 bytes equal 1 kilobyte, often abbreviated as KB. Continuing this pattern, 1024 KB makes up 1 megabyte, or MB, which is commonly used to describe file sizes or memory capacity. Then, 1024 MB equals 1 gigabyte, or GB. Think of this as the standard measure for modern storage devices like hard drives and SSDs. Next, 1024 GB is a terabyte, or TB, which is often used to describe large storage capacities, such as external drives or data centers. This pattern continues with petabytes, exabytes, zettabytes, and yottabytes, each increasing by a factor of 1024. Beyond that, there are even larger units like the brontobyte, geobyte, which are more theoretical or used in very specialized contexts. Throughout this hierarchy, the key idea is that each step-up is 1024 times larger than the previous one. Understanding these units helps us grasp the enormous scale of modern data storage and the capacity of computer memory. And this progression underscores the exponential growth in data we handle today, connecting back to the theme of how digital technology continuously expands our storage possibilities.